Okay. So our second lecture this morning is going to be on particle imaging, and perhaps as sort of a introduction to one of the challenges of particle imaging is you get large file sizes. So I'm going to be swapping back and forth. My iPad's not working right now because it's still like chugging away trying to download all the pictures that are in this very heavy 100 megabyte PowerPoint presentation that I sent to a kid. So that's okay. So we're going to go for maybe 15 minutes or so until they're ready for us outside, and then we'll pick this up again when it's time. So I'm showing here a couple of composite images that illustrate a couple of different, very labor-intensive particle image collection techniques. The set on the left is from Alice Aldridge and Gottschalk in 1988, showing marine snow. And these were imaged and their settling velocities measured in situ by divers. Right? So this is like divers going around with cameras underwater to image the particles in the environment. So labor intensive in one way. On the right-hand side is some images from Clara Flintrop in 2018. And she's also looking at marine snow collected in a sediment trap. Here, this is the lower left-hand image. You can see we're looking down into a gel collector at the bottom of the sediment trap. And what she did was she picked out aggregates, and then she embedded them in a plastic resin, and then sliced them on a microtome, and took image stacks of these physical slices of the aggregate. So that's what you're seeing here. We're blowing up on the aggregate that was picked. Here it is embedded, and then the upper left-hand tile is just showing one thin Z-slice of that aggregate. So again, incredibly labor-intensive, right? These aggregates are of a lot of interest to people who are interested in a lot of things. We'll brainstorm a little bit in a second. But I guess the point I'm trying to make here is that it can be a lot of work to characterize these incredibly fragile, sometimes very large particles in the ocean. And this is just one class of particles that might be of interest. So imaging techniques, in particular, institute imaging techniques, that can be done with instruments, not people, libraries, are of interest, right? Because they can increase our data throughput and the amount of information, spatial, temporal density of what we're recording. So here was where I was going to write down your brainstorm. Actually, it's a little grainy, but I can still probably do that. If you don't mind the question being somewhat. Oh, it won't even let me play or do anything to it. Okay, never mind. We're just going to talk. So why particle imaging? What information content are we gaining? What processes might we be interested in that would make it worth it to take pictures of particles in the ocean? Yeah?
You get a direct measurement of particle size distribution rather than relying on proxy.
Right, so we can get, well, it's not an optical proxy, it's not like an inversion of a volume scattering function, but is it direct? Well, we can come back to this, but what do you measure when you take a picture of a particle? You still have to decide what the size is when it looks like the things I was showing you on the last slide. But yes, you can get a more, you're seeing the individual particle, right? Yeah. Angela?
Is shape also?
Okay. So detailed view of shape. Yeah.
At least 2D.
At least 2D. Yep. Yeah.
In a sense of internal structure.
You can look at the internal structure. Yep. What else can we tell from taking pictures of particles? Yeah.
Their color.
Look at their color. What are some of the things that we can tell from that kind of information?
What they are.
What they are. So when you say what they are, what do you mean?
Species of phytoplankton or
Okay.
just organic matter that's falling.
Okay. So you can say something about what species or maybe the origin if it's not something that's living. Why might this be important? What are some of the things that we do with remote sensing images? You have an A-phi spectrum that you've gotten with an ACS. Is that just cool because it's cool? Like, hey, that's the phytoplankton pigment spectrum. Awesome. What else might you want to do with it?
You can get a better idea for like cycling, budget, cycling, and
Okay.
you know, what's being pulled down and recorded.
All right. So we can use that information to get at cycling things that the phytoplankton are doing. Can we tell what kind of phytoplankton are in the water from some of these IOPs measurements that we're doing?
Link, if you had an image that showed just one type of phytoplankton and a spectrum, you could link that to it being a pure spectra of some sort and use it in decompositions.
Okay. So we could start to, so with our IOP measurements and our remote sensing algorithms, we are interested in community composition of phytoplankton as an example. How do we validate that? Cultures, okay? Yes. So we validate it against things that we've classified, right? Or we can, right? So there's a lot of interest in trying to understand things like community composition and relationships between the ecosystem and biogeochemical cycles from remote sensing and from IoT measurements from proxies. You need to validate that against something, right? And so these imaging tools are increasingly becoming something that get deployed alongside some of these measurements to start to create those connections. Yeah.
The imaging tools are non-destructive, so things like very fragile cells or mucousy items don't get destroyed, and so you can understand their real distribution and abundance as opposed to when you filter it or it came through a pump or it got sucked through a hose really fast and suddenly it's just gone.
Right, right. So they are, I'm going to say they're less destructive, but yes, the imaging tools tend to, they give you a better idea of the in situ configuration of or status, basically, of the things that you're trying to measure with your samples. They're going to get tested. Now I can say, you think. Yeah. So we have, there's a lot of reasons to image particles, right? You can see what they're doing in the water without sampling them and destroying them or modifying them in the process. We can validate some of our remote sensing IoT-based models. We can get a sense for ecosystem structure, processes that affect detrital particles, carbon export, right? Tons of people who are interested in sinking particles and carbon export are using imaging tools to do that. So lots of information in there. So today, what the emphasis is mainly going to be on is particles, mostly that are 100 microns or so and larger. I'll get into why in a second in terms of the physical theory, but also just sort of as a distinction from some of the optical tools we're learning about, which are mostly going to be telling us about particles that are in that smaller size range. Mostly in situ techniques, although I'll do lots of analogies to microscopy because it's familiar and well characterized. And mostly digital systems, although the earliest imaging tools were analog and there was film underwater, all that good stuff. We don't have to do that anymore, mostly. And I'm not specifically talking about remote sensing images, even though we're going to get to that in lots of detail later. So there'll be some things like pixels that will be in common and other things that are going to be really different. Yes? So, yeah, so the IFCB is an example we'll talk about in more detail. It actually does look at particles smaller than 100 microns routinely, but there is a lower size limit. That's actually related to diffraction, and the physical limit of optical imaging. So I'll talk about that. But yeah, a lot of these imaging systems do focus on larger particles because of they have to. And basically, in order to collect all the diffracted light around large particles, you need a large data.
What is that lower limit, like 5 or a little bit below?
The theoretical lower limit, which actually can I get to, well, we're going to get interrupted, so I'll answer your question. We're going to come back. The theoretical lower limit would be if you have blue light and a perfect lens with a really high magnification and a really high numerical aperture, you would probably get down to like a micron, half a micron. But that's like when you, and if you use like an oil immersion lens, you can image something under light that's like a little bit more fine resolved than that. But yeah, there is a limit just based on the physics of diffraction to how small the image will be. We'll first go through just the theory of how these imaging systems work, and I'll try and relate it a little bit to some of the stuff we've been talking about in terms of diffraction and geometric optics. And then a couple of instrumentation examples, mostly focusing on types that are widely used. And then we'll talk a little bit about some of the schemes for particle detection and classification, and mostly how that is fraught, and there's tons of work for people to do in the future with that. Okay, so you've seen the upper panel before, size distribution of particles in the ocean and different approximations, basically, that we can use to model the optical properties of particles in those regimes. So for particles that we're interested in imaging, we're mostly going to be thinking about things in the geometric optics regime, which is basically where we can start to neglect the diffraction of light around the particle, right? And that's going to not limit our ability to detect those particles, to distinguish them from one another, and then down into the anomalous diffraction or Van der Waals regime, we start to get diffraction effects there. Another nice figure came out of a review paper, Vivian Lombard et al. A couple of years ago, that basically imposes the size detection limits of different imaging and a few other particle detection instruments in modern use on the equivalent spherical diameter of particles. And so I lined this up. One's in meters and one's in microns, but did I do it right? I think I'm off by order of magnitude. Oops. Late last night, sorry. There should be a 10 to the -6 difference between them, so scoot it over like one set of power law tick marks. Maybe I'll fix it before I come back after lunch. Anyway, just sort of overlapping those image systems. So we can see we've got a lot of different systems that are out there. They all have these limits in terms of what they can detect and what types of particles they're sensitive to. Is it time to stop?
It's time.
All right. We will come back to this in a little bit.
Now you're in.
Okay. All right.
Super.
I think this should do it. Okay, the students have voted to have a chunk now and then finish after lunch. So, and I think I'm recording, hopefully with sound. So, so this is where we were before. We were just looking at the overlap between the size ranges of a lot of the commercially available particle sizing instruments, many of which are image-based, and our different optical regimes and particle types that we see in the oceans. I fixed the offset there, so they should be roughly aligned in particle size space. Okay, so starting off, we're just going to think about what an imaging system is actually detecting And what is the optical resolution? So what's the theoretical resolution in terms of, how small of features in sample space can a camera or a camera system detect? So what I'm showing here, the cartoon on the screen, is just a representation of a diffraction experiment, similar in some ways to, I don't know if you guys did a two-slit experiment in the lab on the first day of class. You looked at the diffraction pattern around a hair, Charlotte's hair. And we saw the constructive and destructive interference patterns scattering around that hair. So this is different. This is two pinholes or two slits in a barrier, and if you have incident coherent waves that pass through there, they're going to create two diffraction patterns that are going to constructively interfere with one another and create this bright dark pattern on the screen that the light is on the far side. So when we think about the resolution of an imaging system, what we're actually thinking about is how far apart those nodes, the constructive and destructive nodes of the interference pattern are. And that's the limit to what an imager camera system can distinguish. So I've added here a representation of what that might look like if you're looking at the screen and you're looking at the diffraction patterns coming through two pinholes, right? And you can see at the top, in the top representation, those two pinholes are far enough apart that the central maximum and then the minima are clearly separate, right? We can distinguish those two objects. But as we move the objects closer and closer together, their diffraction patterns emerge until we can't tell the difference anymore. So for an imaging system, back in like the 1800s, Rayleigh devised this criterion that the diffraction limited horizontal resolution of an imaging system is going to be related to the wavelength of light and something called the numerical aperture of the lens system. I'm going to use microscopy here as our sort of example system because it's pretty much how all this stuff is defined. And because many of you, I hope, have maybe looked at a microscope at one point in your education, maybe recently, not so recently. But it's a system that we're all familiar with at some level. So basically, if you have light that's impinging, in this case, in both of these diagrams from below on a plane where whatever it is we're looking at under the microscope is located, right? So we're focusing our objective lens on a specimen at the specimen plane. If you think about either just the objective lens's aperture angle, or some microscope systems and some imaging systems that are used in oceanography in situ, there's also a condenser lens that's focusing the incident light down on the specimen plane as well. Those angles are what are going to govern the size of what's called the numerical aperture. So here, this aperture angle we're calling alpha, not related at all to other usages of alpha that you've seen, and you can probably forget about it actually once you understand the concept of the lens aperture. But the numerical aperture is the refractive index times sine of that angle. And you can see by this relationship up here that the larger the numerical aperture, the smaller will be the horizontal resolution of your microscope system. Right? So if you have an angle, if you have a lens rather that's gathering light through a wider angle, it's going to be able to gather more of that diffraction pattern, is a way of thinking about it, and distinguish smaller and smaller features within the specimen from the target of interest.
Then is the index of refraction that of the particle that you're trying to resolve,
No.
or the medium?
No, it is the index of refraction in this distance here. So it's in of the medium between the specimen and the objective lens. So that's another good point. If you have a system where you're looking like a regular microscope in air, right? And then you want to get a higher optical resolution, a higher horizontal resolution, you can increase your lens angle, or like your aperture angle, to a point, but there's a practical limit there. That half angle alpha is, in a lot of lens manufacturers sort of say, okay, the upper limit to that is around 70 or so degrees, right? It's difficult to make a lens that's going to captivate more widely than that. That's a good lens. So the other thing you can do is increase n. You can increase the refractive index. And if you've done microscopy with oil objectives, oil immersion objectives, right? That's what that is. It's you're replacing the air in between your specimen and the lens with immersion oil that has a higher refractive index. It's about 1.5 instead of 1. So that's the other way that you can increase your resolution. The other thing to think about is the depth of field. So you increase your numerical aperture and increase the angle of your lens, you're going to decrease your resolution. You'll be able to see smaller and smaller things, but you're going to trade off the depth of field. And so the depth of field is just defined as the distance in target space, right, in specimen space, between the closest plane that's in focus and the farthest away plane that's in focus. So if you have a very high-powered lens or high numerical aperture, you're not going to have a lot of z distance through which you're in focus. If you, I don't know, play around with a microscope that's got multiple objectives, you can see this by, you can get something that's in focus at a low power objective, look at it, and say, okay, I want to zoom in, switch to a higher power objective, and it's not in focus anymore, right? You have to wiggle it even more, do a little more fine tuning to bring it into focus because the working distance, rather the depth of field of that lens is shorter. So depth of field varies in proportion to 1 over the numerical aperture squared. This figure, which is in terms of the F number, so if you're a photographer, you might have thought about this, which is basically inversely proportional to the numerical aperture. So, so this one is lower in A, this one is higher in A. But I thought this sort of kind of puts together those ideas, that with the higher numerical aperture, you can see these small horizontal details in your system, but the depth of field through which your focus is much smaller than a lower numerical aperture. You can't see the difference in those small details, but there's a larger distance through which so if you're looking at underwater imaging sensors, right, you want to have either, you need to have a system where you can control that flow to make sure that the particles that you're interested in are always going to be in a focal, within the focal distance, in the depth of field of your lens. So, let me back up a second. So if we are working with visible light, and we have this practical limit to how big of a numerical aperture we can have with our lens, and if we say we have our lenses inside of a pressure housing in an optical instrument or it's in water, right? We have this fixed refractive index for our system, right? There is kind of a practical lower limit to the horizontal resolution. If you're working with visible light in water, probably around a micron. For how small of features it's possible to observe with visible light. If you want to get smaller than that, well, you take your sample, discrete sample, and put it under an electron microscope. Electrons have much smaller wavelengths than visible light, so maybe you can start to use that instead. But for visible light microscopy, and that includes underwater imaging, we're limited just by the physics of what's going on.
And we don't go to the UV because it's destructive to the.
It could be destructive to the sample. It's also just harder to make a UV illumination source with kind of power. But yeah, you can photo image things. There are some imaging systems that use blue light on purpose to avoid disturbing the critters that they're looking at near the surface. There are others that use red light because they don't want to get contamination from the sun. The red light's mostly absorbed in the ocean, so there's other things to think about there as well. So UV might cause some other effects as well. Yeah. So ideally, so we've been talking about the lens aperture and the diffraction limit to the resolution of an imaging system. There's also sampling density sensor resolution, right? So I told you this was a slide that the other studies we were out of the room for, but we're limiting ourselves mostly to talking about digital sensors because 2021. I know. But we are talking mostly about a digital sensor that's in the back of your system, right? So you are capturing your image in this array of detectors that make up your usually CCD or CMOS digital image sensor. And you want the camera resolution to match your optical resolution. So it makes no, I mean, I'm showing this purposefully fuzzed out view of a radiolarian cartoon, I think, to illustrate this. But if you have a really good optical resolution, it makes no sense to have a digital sensor that can't capture all of that. Also, you may have heard of the Nyquist sampling theorem in other contexts as well, but you want to capture your specimen or your target at a frequency that's at least twice the frequency of the highest features of interest, or highest frequency features of interest in your specimen. So you're not aliasing patterns, things like that. So going back to our cartoon of the microscope, we have different ways that we can illuminate a sample being imaged in the ocean. If you're interested in imaging in the ocean, pretty much you're going to need a light source, right? Because the light itself, the light will do the trick. That's true for benchtop microscopes too. But you can kind of use microscopy as an analogy for some of the imaging illumination types that we'll see in situ imaging sensors. So the first is just bright field microscopy or transmitted light microscopy. You've got a light source that's shining onto your sample, and then the light that passes through and is diffracted by, absorbed by your sample is what's going to show up in your image. So some examples of things that are in common use in oceanography imaging sensors that use this mode of illumination are the imaging flow cytobot and the flow cam, where the light is passing through the sample. The image on the right-hand side is just an aggregate actually collected with bright field microscopy on benchtop microscope. So then another way that we sometimes collect images, so a drawback of this bright field imaging is that you've got your incident light also impinging on your sensor. So that bright field, right, a light that isn't scattered or absorbed by the sample or diffracted by the sample is also coming into your sensor, right? And you might be interested in getting rid of all of that and trying to get a little bit more contrast, particularly around the edge features of a sample. So in microscopy, we can use something called dark field illumination. And in this case, I put a little, this is just constructed as some PowerPoint cartoons, but you put this red rectangle that I've inserted below the condenser is a stop. It's blocking all the light except for the light that's coming in right around the edges of the lens. So then that edge light is focused onto the specimen plane. And then all we see coming out of the specimen plane is the light that's been scattered at low angles by the sample. So we're not collecting any of that edge light that's out at the edges and not doesn't go onto the detector. And so we see what might be called a dark field image. So there's an example. It's the exact same particle, only Colleen Griffin, who took these images, just flipped the condenser mode, put it into dark field. And so you can see there's a very different level of detail that comes out. It's a little bit easier to see the edges and the internal structures. Some of the subparticles in that aggregate that are opaque and blocking the light are now a little bit more visible. By analogy, the in situ imager that's like this kind of is an underwater vision profiler. It's actually imaging, it's lighting from the sides, and then you see the scatter light that's coming up at 90 degrees. The angle is a little bit different than bright field microscopy, but it's in the same way. You're not seeing the source light, you're only seeing the scatter light. So there are some important differences in the types of images that you get, the different illumination modes. There's also imaging sensors that do neither of these two things that we'll also talk about, including holography and line scanning cameras, which are much simpler kind of in terms of the image collection, but also have some really powerful features. Okay, so it is 12:02, and I'm at a stopping point here before we go into instrumentation examples. So I think this is where we go to lunch, and then we'll come back and talk about the rest after lunch. Okay. Sorry for that little delay. The Zoom meeting quit. All right. So where we left off, we just sort of talked through imaging systems that are used sort of traditionally, like microscopes, and some of the in situ imaging systems, and their commonalities, what limits their resolution, right? Their system resolution, their optical resolution, and the digital resolution of the camera. So now what I'm going to do is spend just a little bit of time talking about some examples of the instruments that are in common use, so ones that you will run into in the literature and maybe are using yourselves, and think a little bit about what are their, how are they calibrated, what kinds of data do we get from them, et cetera. And then we'll talk a little bit about particle detection and classification schemes and some of the challenges that are still remaining. So the first system that I put on my little list of slides here to go through is the imaging flow cytobot, the IFCB, which I'm starting off with, in part because you guys have already kind of gotten into exhaustive close detail with some of the data from the one that's out here on the dock here at Harpswell Sound. But these two figures just demonstrate the principles, basically the configuration of the instrument and what it's doing. So it's a flow cytometer based on actually flow cytometers that originally were invented for medical use, sorting blood cells. But it's been adapted for sorting plankton cells in situ and also imaging them. So the sample comes in through an inlet and enters a sheet flow, which aligns the cells, as Colin was talking about this morning. You're thinking about cell alignment of instruments. In this case, the cells get aligned into a laminar flow through a sample tube that lines them up so one cell at a time enters the optical chamber. So the right-hand side diagram illustrates that intersection. So our sample is coming in here and then passing through the center of this optical chamber, where we have the same optics that we were talking about sort of on a more theoretical level, kind of visible in there. So there's our the xenon flash lamp is the source for illumination of the the image that's collected of the cells. So it's passing through some lenses and mirrors, and then through a condenser lens until it is in focus within the center of that photo cell. Right? And then it enters an objective on the other side, and finally passes through to be imaged in a camera. There's also light that's coming from a diode laser that's inducing side scattering fluorescence. So the flash that illuminates the image collection is triggered by either the fluorescence, if you're trying to get phytoplankton cells, or fluorescence, or it's triggered by the side scattering. You don't care what kind of particle it is, you just want everything that scatters light to be imaged. So for this particular system, there's a 10x objective on there, the numerical aperture, I think around 0.2, and a pretty well matched imaging, so the digital imaging resolution is around 3 microns, as is the diffraction limitation. So this system ends up giving you pretty good resolution, as you can tell, right? When you clipped out all the images and sorted them by size, right? You can size and see particles that are about 10 microns that are occupying a few pixels, but in order to identify them, we need to be able to do that. Also, I should mention, you can see from the way that this is set up, right? This is, as I showed, I think a couple slides back, but it was before lunch. The IFCD is using transmitted light imagery, right? So we've got the green line entering the flow path through the condenser, is passing through the cell and being scattered by the cell. We're picking up what's coming out the other side. So this is sort of analogous to bright field microscopy. Another system that's in really common use is the UVP, underwater vision profiler, which is currently versions 5 or 6, depending on whether you want something that's going on CTE or on an autonomous platform. And this is targeted at a much larger size range of particles. Right? The IFCD has a screen on the inlet specifically to exclude large things. And I think a few hundred microns is probably the biggest you would see there, down to being able to resolve things as small as 10 microns. The UVP is looking at much larger particles, tidal particles, plankton. Things that are below about 100 microns aren't well resolved in this system. The UVP uses side scattered light, so the the photograph and the CAD drawing of just the illumination portion of the instrument are showing this. But basically, you have a camera that's looking down at two lights that are together illuminating from the sides. The horizontal plane is about 3 centimeters thick. So the lens that's being used here has to have a much larger depth of focus to be able to keep everything that's within focus to that 3 centimeters, right? That's a much, it's got a much lower numerical aperture and a greater distance that it's working through. We're looking not at the light that's passing through the sample in this case, but at the light that's scattering off to the side. When you look at images from the UVP, typically, so there's some examples over here in the lower right, typically they're inverted, so it looks like a bright field, right? It's got a white background, dark pixels, but actually you're looking at light that's scattering off of that. So if you imagine looking black or white, that might be something. It's actually red light, but that might be more like what the camera's actually seeing. Because of this sort of large illumination volume, you actually have to calibrate the light volume that's illuminated in each flash that the camera is imaging in order to understand, to get your sample volume, so how many particles per volume. So that's empirically determined, and actually the size, the pixel per micron scale, right? So the size of the pixel in that image is also empirically calibrated. So they use standardized particles in the laboratory, measure them under the microscope, and then measure them in the UVP to come up with a calibration curve like that's shown here. And then there's sort of a standard UVP that all the other UVPs are standardized against. So it's more empirical, and the particles that can be resolved is much larger pixel size that you get out of this.
How often do you need to do that type of calibration? Is this like once a year, or can you move it?
I would imagine it would be a good idea to check every time you move it. A manual actually uses UVPs. How often do you calibrate for size?
So now we're sending back every year, usually because there's no need to do it. And the way it works is they have one gold sensor that they, and I did the process with them once where they actually put it in a large basin and one by one drop eggs that finish realistic particles that you see through the volume and take pictures. And those are sized also separately by line. Then the golden one, when you send yours to calibration, basically what they do is they take a whole like file and do a profile They're very close to deep waters, for about 200 years back in and up, and then they force all senses to agree with it. So if you want, it's cross calibration.
And that's just an alignment, like how the camera's intersecting the light beam.
So that's it, so the
What
characterization of the
context?
volume you're looking is different, and that's depending on the lighting system you use for every lighting system separately. It's, yeah, so that's another issue. But they're very careful to try and make exactly the same for lighting systems. And it's not easy, because we went in the first exports, there were 2 of them, and there was significant bias to one. Which is right one, all language pairs.
So that was an issue, the timing of the flash.
That's what they discovered, that there was one of them, which is ours, that did not, the flash sometimes had only one side flashing and both sides flashing. And since then, they discovered it many other things as well. So it's work in progress, that's all the time gets better. They're all cross-calculated, and now they ask users to send it every day to just check it.
So, like, every sensor is now learning calibration is important. And in this case, yeah, the timing flashes, the volumes of the sample image, and the size calibration of the digital camera, all things that have to be monitored. So I mentioned a couple slides back before lunch that we would also talk about holographic imaging and line scanning cameras as 2 other types of imaging systems that are in maybe less common use for the line scanning, although it's become important as people start to think about larger particles and look sort of higher levels in larger organisms. Holographic imaging is a technology that's been around for a really long time, but is really only in the last decade started taking off, for instance, in marine work, commercial instruments. So the basics of how this works is you have a coherent light beam that's illuminating your sample volume, where all of the light is in phase, right? And an off-axis holographic system, which is sort of the older type, and how you might have made an analog hologram back in the 80s or something. You pass that coherent light beam through a beam splitter and split it into one beam that's impinging on the sample and creating a diffraction pattern. And then another that is just going off a mirror and not being altered at all. In the hologram, the image that's recorded is actually the interference pattern between the light that's diffracted by the sample and the light that is not. And so that 2-dimensional holographic image records all of the scattering phase information that's in a 3-dimensional sample volume. Analog systems, decades ago, would then shine a laser back onto the hologram, and that would recreate the original image. For what we usually, most of the sensors that are in use for marine applications use inline holographic systems. So the bottom panel is illustrating that. And in this case, we just have an incident beam that diffracts around the particles and then interferes with whatever part of the beam has not been scattered. And reconstruction of that requires a numerical reconstruction. It's computationally pretty expensive. So it's also something that's gotten more accessible in the last decade, and it's not something that I'm even going to try and talk about during this lecture. There are some resources that I'm actually going to fill the resource list, the reference list for this lecture. I don't think we have anything put together for it yet, so you guys can dig around in there if you're really interested in the math behind this, but it is quite complicated. Probably something that Kurt can give a lecture if you wanted to.
Yeah, Sequoia makes a list-looking gizmo that's a holographic image of it. It kind of looks like a list.
But it's an inline holographic image, just like this. So the 3-dimensional image of the particle field is basically based on diffraction, right? So we're gonna see the particle size, shape, and orientation if it's an in situ instrument. We're not gonna see its absorption or interior structure as much. We're looking at diffraction pattern. There was a nice review that came out this year, actually like 2 weeks ago, that's thinking about holographic imaging applications in aquatic systems. And it kind of sorts events into the pre-2000s analog era, and then what's been happening more recently with digital holography, which to get the inline sensor arrangement and inline holography that's really easier to implement for an underwater sensor, you really need this digital reconstruction. So the computational advances recently have made that possible. But some of the earlier events that are important include the introduction of it back in 1948. The guy Gabor who did this got the Nobel Prize for it in 1971, so it took a little while for him to get the prize, but it's important. And there was kind of a gap until the invention of the laser in the 1960s, so you didn't have that coherent incident light until then for physical development of that. So the reconstruction of a holographic image, this is the real qualitative version here. Basically, your image is going to be three-dimensional. Think of it as a sort of a Z-sliced image. It's represented here as a sample volume. And you can see the diffraction pattern of one of those slices represented on the forward face of that volume. So the first step is just to remove any artifacts that are due to the particle field in the sample volume. So you can average over time, you can average along that z-axis. So in this example that I'm showing in the middle of the slide here, the background image is just consisting of features that are present in every single slice, right? And so then you get the background subtracted image, which is the one on the right. So you can see in this example, there's a bunch of little spherical particles. They all have this diffraction pattern around them. And like all holograms, every point in that image contains information about the scattering, the diffraction pattern, and every other point of the image. So the whole thing has to be reconstructed in order to get this three-dimensional particle field. So once you do that, that numerical reconstruction, you end up getting a three-dimensional image that's got some particles in focus in one plane and other particles in focus in a different plane, which is illustrated here. So you can't really see the details here. This is at 2 millimeters and 5 millimeters and 10 millimeters going along the z-axis of the image cube. So for instance, up here, 2, 5, 10 millimeters, right? They're just these slices going back. And so you can see that in each slice, there's different particles that are more or less in focus. So a typical step that's taken in a lot of the software is then to go through in the Z direction and pick out wherever each particle is the most in focus, and then collapse that particle so you have a single reconstructed two-dimensional image that brings all the particles from whatever plane you were in focus in to a single plane. And from that point, then you can do whatever particle sizing, classification, etc. you're going to do, and that'll be all of the tools that I'm talking to you about have that problem of classification and analysis. I'm going to treat that in the last section of the lecture. Yeah.
I was trying to make sure my question makes sense logically. Why don't we project it in a 3D computing space and look at it in there?
Well, that's, some people do, actually. So, you're talking about like virtual reality.
Yeah, virtual reality.
Yeah. So I was on a cruise 4 years ago now with a bunch of people. But Melissa Oman has a DIHM digital inline holographic microscope. It's one of the 2 commercial sensors available right now. And she used it, and she brought, so on board we have this computer scientist who did augmented reality. And so we had like literally like VR goggles and like a projection system on board. And we could like look around inside the sample. It was a little tricky. I don't get seasick normally, but I kind of did a little bit when the air marbles inside the ship. So it can be done. I would say it's probably more like if you want to like get numbers out of your particle population and interpret the data, like it's cool, but like faster maybe to like a computer crunch and then make a graph or something. But yes, to answer your question, I guess. Yeah.
So is your delta Z or your Z step limited by like the integration time of the sensor, or is it like based on the amount of light that you need? Like how closely can you space your
Yeah, I think it probably has to do with the image resolution, right? So if you think about like each Z step is sending scattering diffraction pattern, projecting that into the horizontal domain, and so you need to be able to resolve that.
So you still have
That's
the
part
same
of it.
orientation.
It's something that plagues all of these sensors, not plagues them, but you know, a constraint, I guess, for all of them is if your overall scattering by small particles is high enough, then you also are going to mess up the coherence of your incident beam, right? And so you're not going to be able to, there's a limit in that sense as well. So your Z distance might be shorter if you have a highly scattering sample, because you're not going to be able to pass that fluorescence beam all the way through. So I already showed you this slide, and I didn't spend a lot of time on it. This is an example of the application of this to look at particle orientation in situ in the one place where they do this. But there's lots of other applications that are out there. I should say that the advantages of these systems is that they're really fast, like 20 Hz sampling rates. I think is what the list Hollow 2 is advertising right now. And the sample volumes are somewhat small, but you get a lot of information quickly at very high spatial resolution results.
Question from earlier when you showed the slide, you were saying that there's a potential possibility for them to orient themselves back in the angle. But I was under the impression that unless the federal government has some sort of like form of locomotion, they're kind of just like the winds of these water fields.
At larger scales, they are. Like the water moves, the plankton are going to move, but many plankton can orient, they can move slowly, right? And flagellates being one example, right? They can adjust their fluency.
Even diatoms, it's really amazing. You watch those movies of diatoms, you see them, they move, you stop. You move, you stop. You move, you just have to use. They don't have that.
Right.
But they have incredible intricate motion to discover now.
And they orient relative to the fluid environment around them. Right? So on the large scale, they're moving with the current, but if there's shear in the current, it will orient, that will help orient them in a certain
Right.
version.
The last class of imaging detectors I wanted to talk about were blind scanning cameras, or sometimes they're called shadow graph cameras. And I'm going to start by talking about one that's actually no longer produced and sort of old, but it has, there are nice figures in the paper introducing this that I think are helpful to understand how it works. And then I'll talk about a larger format one. So the laser optical plankton counter is one example of this, and it's a very simple, well, simpler system, and that it's really only a one-dimensional detector. It's a line of detectors, so a linear array, and a light source, like a sheet light source, is passed through the sample, and it hinges on the detector array. And then the imager itself is towed through the water. So that's how you get your volume scanning. So you have really rapid scanning back and forth in a plane, and then you measure the size of the objects in sampling volume by towing through it. So the LOPC, you can see in this illustration here, the light is sort of coming out and collimated by a lens, and then it bounces off a mirror, goes through an air-water interface, and is basically interacting with particles in this flow field, and then impinging on this linear detector array here. And the whole thing is moving this direction through the water. Yes?
Does it, having gone through the particles once and then going through a second set of particles again, doesn't that break the fact that we only want one interaction with the particle?
Yeah, I think maybe one side of this actually must be masked from the flow. There's like a tunnel that the water flows through. So I should erase half of the dots.
No, I was just wondering.
Yeah.
I could see one depth, have it go through both so that you got more volume going through or something.
But as you can see, you actually, I'll show you on the next slide, but illustration will kind of clarify. I don't think you want two particles essentially occluding one pixel. So the way that this works, and the reason I wanted to put the LOPC on, just because it's kind of a nice clear explanation, is that you've got the water flow sort of going across the linear detector array. And if you have plankton, like these nice cartoon copepods, going through the field of view across this detector array, different elements of the detector are going to be occluded at different points in time, depending on the shape of the object. So the smaller individual and the larger, I guess that's a copepod, show these two different instances of how pixels 1, 2, 3, and 4, and 10 through 15 are occluded in time as this object with this orientation passes through. And so then you can reconstruct the shadow, or the sort of cross-section of that particle, or that plankton individual from that information. So it's pretty simple in terms of the image, right? And sometimes there aren't even lenses here. You have a very collimated light source. It's not magnified. There's not an objective lens in the same way that there is in, say, ISD or UPP. But you can sample a really large volume really quickly, and that's the advantage if you care about those rare large particles. Remember we were talking about size distributions, how you're limited in your ability to count some of these larger things by just their rarity, right? You have to process a large volume of water to get enough of them to count. Another system that actually just got used during exports, I think, IPSOSIC has one of these, it's the In Situ Ichthyoplankton Plankton Imaging System, or ISIS. Also has been around for a while, is pretty massive instrument, but it operates on the same principle, it's just bigger. So it's imaging 70 meters per second at a 2.5 meter flow speed. So the spacing between the source and the receiver sides of the instrument are much larger. And the point is to image things that are much bigger. And particularly fragile or gelatinous organisms, fish, things that you can't necessarily collect and count in any other way, like in chemical net processing or anything like that. So sort of the very far, large end of the size spectrum in that size spectrum of imaging systems that I showed in one of the introductory slides. This is one of the very biggest things. Okay, so that was just a handful of imaging systems that are out there, mostly kind of organized by the type of sensor that they use. There are many, many more. This is not an exhaustive treatment in any way, but just to give you an idea. So one thing that all of these instrumentation systems have in common is that they're going to produce an array of images that have to be analyzed and interpreted, sized, identified, what have you, in order to get at the scientific question of interest. And this is where there's still some really big challenges facing our field. So at sort of a basic level, all image analysis of imaged particles consists of one, finding the particles in an image that may have many particles represented, measure or identify or otherwise classify the particles, and then interpret the data. This is one example of a schematic that is in a paper that I'm a co-author on. This is probably almost out soon. I can send you the bioarchive link if you're interested in the details. But it's an example of the many steps that happen between collection and interpretation. In this case, it's just looking at the size distribution, right? The end product in this particular flow chart gets you a number flux size distribution. But there's a lot of choices that have to be made along the way, a lot of classification decisions that have to be made along the way. And anytime somebody is generating information or generating an interpretation of this kind of image data, they need to be, they don't always, but they need to be talking about those choices that were made, about how they found the particles, how they measured the particles and identified them, in addition to the usual how do you interpret the data type information. There's a lot going on here, but this is an example of one study recently published by Sarah Gearing and a SCORE working group on basically the interpretation of marine particle imagery, looking at the effect of how you find the particle in the image. So how do you identify the edge of the particle and figure out what part of the image is particle and what part is not? There's a lot of different algorithms out there for how you do this. One method is just a simple threshold method. So determine there's, what's the pixel value from completely white to completely black? What's the pixel value that is particle and what is the pixel value that is not? So what's the background? Anything above the background is particle. How do you count that? So they're looking at different algorithms. I think you can probably see in this column that there are massive differences in what areas are included in the particle that's detected. And they're just comparing everything to one threshold algorithm just so that they're kind of doing everything relative to the Otsu algorithm. There's also particle finding algorithms that use, instead of just looking at the absolute level, the pixel gray level, they look at the variability through the image. They look for high variance regions, and those are the edges of the particle. So there's 4 more. This is the continuation of that same table I showed you on the last slide. So here are some more outcomes of these different algorithms, right? So these different, these are now edge detection algorithms for finding particles, right? So if you're finding particles in an imaging system, you need to talk about how you found them in the first place. What algorithm did you use? And in this comparison, in the Gearing 2020 paper, they found major differences, right? Just in how you assign what is particle and what is not. How continuous are the edges of a region that might be a particle? Is it one particle or is it a bunch of them all stuck together, right? Those kinds of things will all come out of your edge detection or your thresholding algorithm. This is just looking at the relative equivalent spherical diameter of particles that are detected with all these different algorithms. Yeah. The imaging flow cytobot particle sizing algorithm includes a middle step, which is computing the phase congruency, which is basically looking for, it's doing a Fourier transform on the image, basically looking for places where you've got these phase contrasts in the image. But this seems to improve the performance of a threshold-based edge detection algorithm. And so you end up getting a less ambiguous edge detection. So this is just from the imaging flow cytobot data. You started applying this to other imaging sensors. I don't know if it would work as well or in the same way. So that's sort of another question. Does the same sequence of processing steps work across these different illumination and particle imaging platforms? So assuming you can consistently identify and pick out your particles, segment them from your image, then you need to identify them. Say, hey, what are they? how can we reduce this to a data set that we can use to answer the scientific questions of interest. Machine learning is sort of one of the rapidly growing classification techniques. I'm not going to go into the details there. We teach a whole course. Whole courses have been taught on this, and I am not an expert in it. But I wanted to show one example. This is again using IFCP data and comparing two different machine learning approaches. One that's training the machine learning algorithm to correctly identify individual images, and then another algorithm that's training it to correctly assign the right proportion of classes across a sample, right? So getting the sample composition right versus getting all the images in the sample in a yes-no sense, right? And it turns out, in this example, the purple line is classifying images based on just classifying images in order to generate the correct sample composition. That's the purple line. The blue dots are the manually expert classified, person looking at a microscope ground truth, and then the blue line is if you train the algorithm to just try and get every single individual image, right? So it suggests there's sort of some interesting directions to go, particularly if you're using this kind of data to answer specific questions, like what's the composition of my sample, you can do a better job than if you're just trying to stick a name on everything and then count it. Another challenge, and this is again from seismic track work on exports, is what if you have fuzzy boundaries of your particle classes? So, something, if you're trying to identify a species, right? There's sort of a defined, this is the entity, this is what it's called, here's how you identify it. But particularly like the top 4 categories that are shown in the image collage, A, B, C, and D above. These are all individual particles identified manually from manual microscopy. There's sort of a continuum as you go from a degraded, loose, falling apart aggregate all the way to a fresh, intact fecal color. You need to see some pictures of food, right? So what if the classes aren't distinct from one another, right? There's a whole different problem that arises there. And this may be especially true if you move into the physiologic or away from just looking at phytoplankton, well-defined classes. Finally, a question that I think came up on our slide at the very beginning was how do we, we might be interested in imaging particles because we're interested in their composition, we're interested in their carbon content or their biomineral content or something like that. And even things as simple as how do we get from the area that we see in an image, assuming we can use the right algorithm to figure out what's particle and what's not, and actually segment it. How do we get from that projected area in our image to a volume? And then how do we get from a volume to a carbon content, right? There's lots of questions there too. The example here is just illustrating, are you even looking at just the cross-sectional area that exceeds some threshold, or are you filling all the holes in your cross-sectional area, assuming that the particle is solid, right? Completely composed of the same thing. A couple of different particle area to volume approaches are shown here. The top half, the Moberg and Sozek, is coming up with a mathematical method for converting the area of the particle to a 3-dimensional shape based on the distance of every interior pixel in a particle from the edge of that particle. So this is a way of trying to assign 3-dimensionality to images of phytoplankton. The bottom part of the slide is the same sediment trap particles I showed you before. And then you don't have to look at the details of this table, but it's basically just a table listing the geometric shape that was used to model the volume of every particle class on the right-hand side. And how do we parameterize its width and length as a function of its equivalent spherical diameter? How do we convert that ESV to a volume? And then how do we convert the volume to carbon? And all of those conversions are either based on observations or on literature values for particle volumes or different types of particles. So you can see you quickly can explode the number of parameters that you need to do these transformations. And yet every time you're doing this, you're taking an image and converting that into some real thing that you're trying to answer questions with. You need to document those steps and justify the choices you're making. So it can get pretty complex, and there's a lot of work left to do. So this is just returning back to that original flowchart about all these steps. So some take-homes, I think people are ready to get up and stretch their legs and learn some modeling soon, are that imaging techniques definitely are providing important information, validation for some of our other optical sensors. There's a lot of needs for the future, including sharing details of these methods, and coming up with standardized ways of comparing one sensor to another, sharing classification tools, developing classification tools that are consistent from one sensor to one sensor and from one environment to another. And this is going to require a lot of collaboration, obviously. But that's cool, because we're all here.
Yeah.
Yeah. That's it.
As spheres.
Or we can just call them all homogeneous spheres. That's what we're going to do next. So I think, how long do you want to?
So just to add to this, the part of the sensor is also just like you can access, UGCR approach, you'd be able to access images. And there's several efforts, one of which is, you mentioned it before, people that French efforts, to the point where they cannot post the data for the rest of the world. So there's efforts in the US to figure out platforms as well as how we're going to use the same software, different software, but if they need it, then everybody can access everybody's images. Then they have much more value. Each one has its own.
That reminds me, there's a list of references, including links to ecotaxa and some of these tools that are being developed for image analysis. But there was a web conference that happened a few weeks ago on pelagic imaging, basically, and a lot of the people who were working on the cutting edge in these kinds of things gave short talks. And so I've got this long list of YouTube links to their talks, as well as a long list of links to things like ecotaxa and some of these efforts to internationalize these different classification schemes that I will put on the student drive. Maybe I'll put it in the reference folder. I'm not sure where the right place to put it is, but kind of a nice resource if you're interested in these kinds of tools to check out.
And it's also critical for us when we try to express remote sensing, because there's a big push to try to boost in space. With upcoming hyperspectral method, hyperspectral missions like space, and within hyperspectral missions. And the true validation is not going to be visuals. True validation is, can we actually see that the organism contains these data transactions? And so for this is why NASA is so interesting. As we move to more sophisticated products like diatoms and data plasmids, are they supported with data? And people have already published them, or science divisions, but they're not validated. And so you need the validation.
So NASA just had a big effort, part of a workshop, a working group that to try to figure out how to upload data from these different sensors into a database, much like we upload absorption or backscattering. And so, it's so much more complicated because you can't just upload the size distribution or someone's algorithm for biovolume. You have to upload the images. And so where do the images sit and how do you get to them and how they get classified and what version of what program would they use to classify them, sort of finding the provenance of those images. And so it come down to basically providing every image with some URL. So every image that you guys cut out has its own URL. And it's linked to a serious metadata file, which says, where that sample was collected, what were the settings of, say, the IFCB when it was collected, and what version of the classification program will identify this as a diddler. And you used a different classification scheme, what they call it. And so all of that information is now going to be to us, which is pretty exciting to be able to have all the flow cam data, all the IFCB data, any microscope data, any sort of imaging data in a single space, so that you go out and run an algorithm and you're like, I can get tuned from your data tons with my algorithm, and then you can validate it by going into the databases that are not just for you and identifying how many tuned from data tons were in fact in the sample. So it's pretty exciting that NASA has taken this on, and that people who do this kind of work were the integral part of making sure that the important information is passed along with these observations. So it's really fun to be a part of, to watch that happen.
Was there a web page or data source set up after or during that process that you were talking about?
Yes, and there's a paper coming out, the last draft just came across email, and in fact, we just are doing the last read on it before it's submitted. And then it will be free for you. Love NASA.
So yeah, whatever, 5, 10 minutes straight.
About
You-
2 o'clock.
You're ready to cram information into your brain.